Of these solutions. And the first two I have up here are 52 and 54. Hello there. I did do a homework check. If you want to grab that, I'll look at it here in just a second. Why don't I actually kind of go through these first, and then I'll maybe run back through all the other answers. So we'll eventually talk about each one. But 52 was the first one that I thought may have caused a few issues. It's got y equals cosine of the quantity 1 minus 2x squared. So it's cosine of something other than x, which means when we take the derivative, you can call it y prime or dy dx, you will have to use the chain rule for trig functions. It's not the entire cosine being squared, it's just that last part that's squared. So what was the derivative of cosine? Negative sine. You take the derivative of just the trig function, so there's that. Now I have to come back and take the derivative of the part after the trig function. And that is also going to require the chain rule. This is like the original chain rule where you pull the power out front, make it to the one less power, and then come back and take the derivative of the part in parentheses. So that would be a -2. Now, single terms. That's kind of like a -1 right there. You can draw that in if you want. -1 times 2 times -2. We may have had something similar to this in the notes yesterday. That is a 4. Now, right after that, I'm going to put this quantity because it's not with a trig function, and I like to move all that stuff to the front. And then sine of 1 minus 2x squared, that part would move to the back. If you wanted to distribute the 4, you could. You would only distribute it to the first quantity. Mrs. Chappell has it down there if you want to go ahead. Thanks. Okay, 54 is the next one up here. Now, in the book, I'm not sure how they wrote it. I wrote this as secant of 1/2 theta, tangent of 1/2 theta. 1/2 theta is the same as theta over 2, so I'm not sure how they wrote it, but I kind of like it written like this better because it's got the 1/2 in front. Theta is like the x here. So when I go to find the derivative of this, we had one similar to this in the notes yesterday. There is something with theta times something with theta. So I start this with the product rule. 1 is just secant of 1/2 theta. D2, derivative of tangent, is secant squared. So I write that as secant squared of 1/2 theta, but then I have to come back and take the derivative of 1/2 theta, which is 1/2. I should write smaller here because I've got a little bit more to do. So this is 1 D2 plus 2. We'll see if I can squeeze this in. D1. Not going to squeeze it in, but that's all right. D1 right here, derivative of the secant of something is secant of the something, tangent of the something. So I'll start with secant of 1/2 theta, tangent, I'm going to have to go down to the next little part there, tangent of 1/2 theta, but then I still need the derivative of 1/2 theta, which is 1/2. Whole lot going on up here. 1 D2 plus 2 D1. Derivative of secant is secant tangent, so it shows up twice. I put parentheses around the whole thing right there. I guess it doesn't really matter. It's all getting multiplied anyway. So looking up front, I'm going to pull the 1/2 to the very front because it's like the only part that does not have a trig function with it. And then thinking of that as secant to the first times secant squared, that would be secant cubed of 1/2 theta. So I would multiply those together, and then I'll kind of do the same thing in the back. Pull the 1/2 out front. There's only one secant of 1/2 theta, but there's two tangent of 1/2 thetas. So I guess I don't have to put parentheses around the whole thing. Tangent times tangent, that would be tangent squared of 1/2 theta. If you wanted to pull something out front, you could. I may just leave it like that though, since there's no denominator, it wouldn't really reduce. Okay, a lot going on with 54. Any questions about that one? All right, well, I can't remember which one's next here. 58 and 60, and then if there's any others that you've got questions about, we can do those too. We are going to plan on a quiz Monday over 2-3 and 2-4 along with binders. We'll talk more about that later, but I am thinking, and I'm not sure if it's exactly like this, but I am kind of thinking that there's a problem similar to 58 on the quiz, if my brain serves me correctly. So this is a good one to go over. Now, because of the square right here, this is like taking 5 times the entire cosine of pi t squared. Pi t, but that whole trig function is being squared. So when I go to do my derivative, it starts with the original chain rule. You have something with variables raised to a power. Pull that power out front. 2 times 5 is 10. Make it to the 1 less power, but then you have to go back and take the derivative of the part in parentheses. And this is where we have another chain rule, but this would be considered the chain rule for trig functions. So let me just kind of start another little set of parentheses here. And derivative of cosine is negative sine. Leave the pi t alone, but then go back and take the derivative of pi t. Kind of sounds like potty almost. Pi t, and that would just be pi. So think of this as a -1 right there. 10 times -1 times pi, that would be -10 pi. And it doesn't matter to me what trig function you put first. If you want to just leave it in the order it's given to you, you can. Parentheses, you can put it around the entire trig function like you have it up here if you want, or if you want to leave those off, it may still be a good idea to put them around the pi t part. So chain rule inside the chain rule on number 58. Now 60 is the next one up here, and then we'll kind of go back through and look at the other answers. So before I do the derivative here, let's think of this as cosine of the entire thing, 8 theta, that entire cosine is being squared. It's actually similar to 58. I'm going to pull my power out front. make it to the one less, come back and take the derivative of the part in parentheses. Derivative of cosine is negative sine, but then derivative of 8 theta is just 8. So this actually did work a lot like 58. 2 times negative 1 times 8. We'll just pull a negative 16 out front. And then you've got cosine of 8 theta, sine of 8 theta. You can put the sine first there if you want to. Okie doke. Questions about either of those? I'm going to spend a lot of time on homework today again, but that's all right. Now, I'm going to backtrack a little bit here, maybe run back through the other answers. I don't know if the back of the book is different on some, so I'll just go through each one. 47 should be negative 4 sine of 4x. Number 48 should be pi cosine of pi x. Okay, 49 is 15 secant squared of 3x. 15 secant squared of 3x. Number 50 ends up being 2x secant of x squared tangent of x squared. Okay, 51, I don't think I had this one up here earlier. For 51, you start with the chain rule for trig functions. Derivative of sine is cosine, so I put cosine of pi x squared, but then you have to go back and take the derivative of pi x squared, which is the chain rule again. Pull the 2 out front, make pi x to the 1 less power, and then derivative of pi x is pi. So it might be helpful to put a little bit down up here real quick about number 51. It was sine of pi x squared. So let me just kind of put up here what I just said. It's a trig function of something other than x. So this is chain rule for trig functions. Take the derivative of the trig function, leave everything after it the same, come back and take the derivative of the part after the trig function. So for this, I need the original chain rule. I'll pull the 2 out front, make this quantity to the 1 less, and then come back and take the derivative of the part that was in parentheses, which is just pi. And here's how I wrote all of that stuff together. You have a 2. Now pi times pi, it might be easiest to write that as pi squared if you want. I'm not sure what the back of the book did, but that would be easiest. And then you also have an x with that stuff. And then right after that, I can put the cosine of pi x squared. That's probably our best answer there on 51 question.
Why can't you just do that one like 58?
58, good question. It goes back, and I'm going to put 58 right above it here. It was g of t equals 5 cosine squared of pi t. Okay, this is different because with this function, the only thing being squared is the pi x. The sign is not being squared, it's just that quantity. But on this problem, because the square is like right there in the middle, it's not that the pi t is being squared, it's that the entire cosine of pi t is squared. So the difference is just the square. With that one, it was around the entire trig function, but with this, it's just around the part after the trig function. So you do this starting with the chain rule for trig functions. That is more original chain rule where you've got a quantity with variables raised to a power. Yep, that is kind of tricky there. It all depends on where the square is. Where is the square? Okay, so 51 is done. We also already did number 52. So with 53, you hopefully use the product rule, 1d2 plus 2d1. You can leave that as -2 sine squared of 2x plus 2 cosine squared of 2x. If you want to pull something out front, you can, but again, -2 sine squared of 2x plus 2 cosine squared of 2x. All right, 54 we already did, 55 you skipped, 56, hopefully you did that one like the last one in the notes yesterday. Rewrite cosecant as 1 over sine, and then you just do the product rule. That one ends up being cosine squared of v minus sine squared of v, and you can just leave it like that. 57 ends up being 8 secant squared of tangent of x, 8 secant squared of x, there we go, times tangent of x. So 57 is kind of like 58, where you had an entire trig function to a power. 59 is similar, an entire trig function to a power. That one, 59, ends up being 10 tangent of 5 theta secant squared of 5 theta. All right, 60 was already up there. 61, again, you've got an entire trig function to a power. Once you simplify that one, actually the 2 and the 1/2 kind of drop out, and you just get sine of 2 theta, cosine of 2 theta. All right, and then 62, very last one, might be helpful to kind of look at this one up here as well. 62, it had h of t equals 2 cotangent squared of pi t plus 2. It is an entire trig function being squared. The 2 can stay out front, but the entire cotangent of pi t plus 2 is being squared. So chain rule, original chain rule, something with variables raised to a power. I'm going to pull the power out front, make my new power 1 less, so that's just a 1 now. But then I have to come back and take the derivative of the part in parentheses. Derivative of cotangent is negative cosecant squared. This is the chain rule for trig functions right here. So I leave the part after it alone. So it's negative cosecant squared of pi t plus 2. But what will I have to put right after that? Anybody know? Yeah, and that would just be pi. So chain rule inside the chain rule, again on this one. So 4 times -1 times pi. Let's make that just a -4 pi. And then I'm just going to leave cotangent of pi t plus 2 cosecant squared of pi t plus 2. That is 62. A lot of stuff going on there. Any questions about other stuff on that assignment? If it makes you feel any better, I kind of think that the chain rule, especially the chain rule with trig functions, is one of the hardest things that we'll do in calculus. Some things may get harder, but for the most part, I kind of think that this is pretty complicated. So if you're struggling a little bit, That is fine. That is normal. We'll still have some time to work on it. So hopefully that helped clear up some questions about the homework. And I'm going to go ahead here. This is part 4 of section 2-4. And I'm going to give you a few more derivatives today. Maybe just yeah, there's a few. And right now, we're going to talk about derivatives of exponential functions. Derivatives of exponential functions. The first exponential function that we're going to talk about is e to the x. Now actually we've already had this part, so this is kind of review right here. Do you remember what the derivative of e to the x was? E to the x, very good. So that's just the same. Now what we're going to get into a little bit today is when this exponent is not just x, it's something other than x. So right next to this, I've got a different function which says e to the u power. Now you need to know that the u right there is just a function of x. It's not just x. It might be 2x, it might be 3x squared, it might be x plus 2. It's something other than x. And so here's how you take the derivative of that. It's going to be, this is f prime right here, it's going to be exactly what it started out as, e to the u power, but then you multiply that by the derivative of u. It's kind of like the chain rule, how you had to go back and take the derivative of the part in parentheses. Now we have to go back and take the derivative of the exponent, whatever it was. Okay, this should be much more simple than doing the trig functions. So this is hopefully going to be a refreshing lesson today. And the directions, probably for all of them, are just going to say to find the derivative. Find the derivative. Here is example 1. We've got f of x equaling e to the 2x minus 1 power. E to the 2x minus 1. This is not just e to the x. This is e to some other function of x. So the u here is the 2x minus 1. So when I go to take the derivative, remember it said the derivative of e to the u was e to the u. So I'm going to put exactly what they gave me down first, but then I have to multiply that by the derivative of u. So derivative of 2x minus 1 is 2. Now to make that look better, we'll probably want to pull the 2 in front and just write it as 2e to the 2x minus 1 power. That is it. You leave it as e to the u, you go back and take the derivative of u. All right, let's keep moving here. Example 2, f of x equals e to the x squared. It's not just e to the x, it's e to the x squared. So this is the u again, x squared is u. So leave it as e to the x squared and come back and take the derivative of u. So derivative of x squared is 2x. And now I'll just kind of pull that out front like I did on the last one and just write it as 2x e to the x squared. Okie doke. I've got one more here with e, and then we'll switch over to something a little bit different. Number 3, f of x equals x squared e to the negative 5x power. I see the e part up there, but there's an extra part in front. Anybody know what rule we're going to have to use here? Product rule. Something with x times something with x. So 1d2 plus 2d1. 1 is just x squared. d2, derivative of e to the negative 5x, is going to be e to the negative 5x times negative 5, because that was the u part. Okay, 1d2 plus 2, which is e to the negative 5x, d1. Derivative of x squared would just be 2x. Now, with the first group right there, you can take x squared times negative 5 and write that as negative 5x squared. And I usually like to move my negative exponents to the bottom so that they have a positive power. So I'll probably rewrite that first part as negative 5x squared over e to the 5x. And same kind of thing back here. 2x can stay on top, but you can pull e to the 5x to the bottom. And now we have common denominators, so we can just keep e to the 5x on bottom and go ahead and just turn that into one fraction. Negative 5x squared plus 2x all over e to the 5x power. Back of the book on some of these, for some reason, doesn't fix the negative exponents, but I think it's a lot nicer if you do, so we'll probably try to do that if you have a negative exponent. All right, that's probably all we need with e. It's pretty simple, just as long as you go back and take the derivative of the u part. So the other type of derivative that we're going to have today, and thinking about your quiz on Monday, you may want to put some of these rules and stuff on your cheat sheet. It can be a half cheat sheet, one-sided. But we're also going to have some natural log derivatives. So let me start with just f of x equals natural log of x. Okay, it's just x. To take the derivative of that, f prime of x, it's going to be just 1 over x. Derivative of the natural log of x is 1 over x. Now I'm going to put a little condition out to the side because technically, and you do not have to copy this graph down, but technically with a natural log function, the domain is only good for x's greater than 0. So I'll put that there, but you know, anytime you actually use this derivative, you're not going to have to write that every time. But that is just kind of a technicality there that we always have to say about the natural log function. Now, what if it's not just x? What if it's natural log of something other than x? So again, the u here is a function of x. To take the derivative of the natural log of something other than x, we're going to take 1 over u, kind of like we had 1 over x on the other side, 1 over u, but then we're going to multiply it by the derivative of u. So derivative of the natural log of x is just 1 over x. If it's something other than x, it's 1 over u times the derivative of u. Kind of works the same way as exponential functions. Now because, I'm going to go ahead here with number 4, Because these are logarithms, we might be able to use some of our properties for logarithms on some of these problems. We'll just kind of see what happens here. So, number 4, it says f of x equals natural log of the quantity x squared minus 1. This right here is the u part. This is the natural log of something other than x. So to start the derivative, there's a light that's flickering over there, a little distracting. To start the derivative, we're going to take 1 over u, so just 1 over x squared minus 1. And then we'll have to come back and take the derivative of the part that was u. So derivative of x squared minus 1, that would just be 2x. So to make this look better, you can think of the 2x over 1 if you want to. And then that would, once you kind of multiply that together, that would turn into 2x over x squared minus 1. That would be our derivative for number 4. Okie doke. Now I'm going to keep on moving here. Stop me if you have any questions. Number 5, y equals, it's the entire natural log of x squared. What rule do we always use when we have a quantity with x's raised to a power? Chain rule. So for the derivative here, I'm going to pull the power out front, make it to the 1 less power. That would be like the natural log of x, all of it to the first power. But then come back and take the derivative of the part in parentheses. Derivative of natural log of x is just 1 over x. Now, there's different ways that you could write this answer. I took the 2 over 1 and kind of just multiplied it with the 1 over x and wrote it as 2 over x, natural log of x. Or if you wanted it to all be in the fraction, you can kind of think of the ln of x over 1. You could also say 2 natural log of x over x. That's just 2 different ways to write it. Okie doke. Moving here. Number 6, almost cut it off, but it's barely there. Number 6 says f of x equals the natural log of the quantity x times the square root of x squared plus 4. Now, there are different ways to do this, but I want to show you a shortcut. It goes back to some of our logarithmic properties. Anytime you're taking the log of a product, you can separate that out using what sign? A plus or a minus? Product property. Plus sign. This was from, well, we may have done it a little bit in chapter 2, but this is a lot of pre-calc right here. The natural log of a product is the same for this. It would be the same as the natural log of x plus the natural log of x squared plus 4 to the 1/2. I changed that from a square root to a 1/2 power. Now, when you take the derivative of a sum, you can just take the derivative of each part separately. So what was the derivative of natural log of x? 1 over x. And then, actually, there's something else we could do in the back here. You wouldn't have to do this next, but if you want to use the power property also, you could pull that 1/2 in front of that quantity to kind of get rid of the power right off the bat. If you don't do it this way, you would end up getting that 1/2 from the chain rule later on. It's not a step that you have to do at this time, but there it is. So derivative, again, for the natural log of x is going to be just 1 over x. And coming back here to the second part, leave the 1/2 out front. We called that the multiple rule a long time ago. Anytime there's a number in front of your function, leave it there. And then take the derivative of this part. This is like the natural log of u. So I start with 1 over u. So 1 over x squared plus 4. And I'm going to multiply that by the derivative of u, which would be a 2x. So you can probably just leave the 1 over x out front. And then multiplying these fractions together, the 2's would actually reduce out. Those would just drop out there. And now you really just have x over x squared plus 4. You could get common denominators. There's nothing really obvious, though, that they have in common that would make that really easy. So this would be fine to leave it separate. Okie doke. Stop me if you have any questions. I think there's 2 more here. And we may try to use some more properties. At least with this one, I think we can. It's the natural log of 3x squared over x minus 2. Natural log of a quotient. This is the quotient property. Product property used a plus. So quotient property is going to use a minus. This is the same as the natural log of 3x squared minus the natural log of the entire quantity x minus 2. Now, I can't use the power property right here with the 2 because the only thing being squared is the x, not the 3. So I'm just going to leave this the way it is. That'll be u for the first part. That'll be u for the second part. And here we go. I'm going to take 1 over u, so 1 over 3x squared times the derivative of u, which is 6x. And then minus 1 over u times the derivative of u, which is just 1. Probably don't have to put it there. Now, simplifying this, you can think of the 6x over 1. Divide by 3. That 3 on bottom will drop out. Now you just have a 2 on top. X, you can divide by x on top and bottom also. So you end up with just 2 over x minus 1 over x minus 2. Again, if there's something in common that would make the common denominators pretty simple, go ahead and try it, but for these mostly, I'll probably just leave them separate. Okie doke. Now, if you look at number 7 real quick, back to the original function, the entire fraction was with the logarithm. Keep that in mind as you look at number 8, last one. The logarithm is not with the entire fraction. It only has a logarithm on top. It says natural log of x over 3x. So you can't use your quotient property for logs where you separate that out. If it was like this, Sure, you can do natural log of x minus natural log of 3x, but again, it's not the entire fraction with the log. So, anybody know what rule we're going to have to use here? It's a quotient rule. Yeah, you have something with x divided by something with x. So, ho-de-hi minus hi-de-ho all over ho-ho. Here goes nothing. Ho is 3x. D-high, that would be 1 over x.
Okay, at this time, those students that are going with Ms. Sparks to Vincent University for a field trip are dismissed. I think your bus is going to be on the bus ramp. So those students are taking a field trip. Thank you.
All right. Ho-de-hi minus hi d-ho, that would just be 3, all over ho-ho. By the way, when you square the 3x, since it's just 3x, not 3 plus x, or 3 minus x, you can just square the 3 and the x separately. Now, we will try to make this look a little bit better. Right here, you may want to think of that 3x over 1. So the x's can drop out right there. You end up with just 3 minus, I'm going to pull that 3 out front so I'm not tempted to multiply it by something I shouldn't multiply it by, all over 9x squared. Only thing I would do here now is, and I can do this because they all have it in common, I would divide everything by 3. So 1 minus the natural log of x all over 3x squared. That looks good there for number 8, quotient rule. Any questions about that? All right, so this is C42 here from page 168 to 169. I won't be here tomorrow, but I'm going to leave my answer key out for this assignment. So your job tomorrow is to finish the assignment. If you don't get it done before then, check your answers. The sub will have the answer key up here. And then quiz Monday. I'll still have some time at the beginning on Monday to answer questions if you didn't get them answered tomorrow. So we'll still do that before the quiz. But you also may want to make your cheat sheets tomorrow, organize your binders tomorrow. So tomorrow's kind of a work day.